Today we're going to be talking about decay in elements. Objectives today: we want to explain how a transmutation happens, describe the three types of radioactive particles, predict the outcomes for all three types of radioactive decay, and we want to learn about the transuranic elements. Transmutations. The changing of an element to another element. Well, to start off with, I want you to understand that uranium has 92 protons. Get my pen to work here. It's going to start off with 92 protons. Well, what happens is when it decays, an alpha particle is emitted. And what this means then is it no longer has 92 protons. This is now down to 90 protons, and this alpha particle, it's going to have 2 protons and 2 neutrons. Well, it's gone down. It went from 92 protons to 90 protons. So it's no longer the same element. It was uranium. It's now 90 protons, which makes it be a different element, and this other particle, which we call an alpha particle. And this right here is the alpha particle. During a transmutation, energy is released. So when they split, the energy is released, and what we have is gamma energy, kinetic energy of the alpha particle, and kinetic energy from the thorium. So back here, I believe that 90 protons makes this be the thorium. I just realized I didn't say that. So the alpha particle is going to have kinetic energy. The thorium is going to have kinetic energy. It's moving. And we're also going to have this missing, or this gamma energy. Well, what I want you to understand is that the mass numbers are still going to balance, and the atomic numbers are still going to balance. The mass number of uranium was 238. The mass number of the thorium is 234. The mass number for the alpha particle is 4, meaning this, it had 2 protons plus 2 neutrons. Up here it had 92 protons plus 146 neutrons. And then this 234, it has 90 protons and 144 neutrons. Well, what I want you to see is that the protons, the atomic numbers, still balance. 90 plus 2 is 92. And the mass numbers, they still balance. 144 plus 2 gives me 146. So we don't lose any mass here. So the mass is going to be the same. This new reaction, thorium, is radioactive still. Right? The uranium was radioactive, and that's why it underwent alpha decay. When we say decay, meaning it lost an alpha particle. Thorium is still radioactive, which means it's still going to have a decay. What we find out here is beta ray is released, and a neutron becomes a proton. We're going to talk more about this beta decay in a short bit. Let's talk about the alpha particle. The atomic number changes. If you emit an alpha particle, our mass number decreases by 4. Why does it decrease by 4? Because we lose 2 protons and 2 neutrons. So there are 4 less units in the mass, in the atomic mass, in the nucleus. Sorry, not the atomic mass, but in the nucleus, which is where our mass number comes from. The atomic number decreases because we lost 2 protons, and we have this new element that's present. And that's exactly what happened up here when the uranium became thorium. We emitted an alpha particle, the atomic number went down 2, and the mass number went down 4, as we've shown in our examples. Penetrating power of an alpha particle. An alpha particle has the least amount of energy, and it's fairly easy to stop. Typically what happens is an alpha particle will grab a few electrons, and it just simply becomes a helium atom. Why does it become a helium atom? Because helium is in the last row of the periodic table, that's over here, which means it has 2 protons and 2 neutrons. Well, that's what an alpha particle has. So an alpha particle is just simply a helium atom, or a helium ion, and then because it's an ion, it's a helium ion of probably +2, not probably, but is +2. It'll grab a few electrons, and it simply becomes helium. It's not very hard to stop. It doesn't have much penetrating power. An alpha particle is not dangerous. A beta particle. We had talked a little bit about the beta particle. All right. Emitting a beta particle. Well, thorium, we said, is going to go through beta decay. The atomic number is going to increase by 1 because what happens is the neutron decays and it becomes a proton. Well, the proton is going to change the atomic number. It's going to go from 90, such as thorium, and if it emits a beta particle, it's going to gain a proton, so it's going to go up to 91. The neutrons are going to decrease by 1. So there's 1 less neutron. So the atomic number goes up +1, but the mass number does nothing. It stays put because the proton simply becomes a neutron. The neutron simply becomes a proton. So nothing is going to happen to our mass number. We still have the same number of elements in that nucleus. An electron is emitted. The electron takes off, and we have a new element. So decay, beta decay, is when a neutron becomes a proton and an electron is shot off. Penetrating power. Well, this is faster than an alpha. This should be alpha particle. And it's attracted to the nucleus. It'll travel until they stop and then become part of the material they're in. So it does have more energy. Typically, it's going to take off and it's going to be attracted to some other nucleus that has some other ion that is positive because obviously the electron is negative. Gamma particles. All right, these gamma particles, these are going to be emitting. There's no change in the element. There's just lots of energy. As we talked about last trimester, or last unit, the gamma, if we talk about the electromagnetic spectrum, started with, is it radio waves? I think that was the first one. And then the last one was gamma. So we said radio waves had low energy, and gamma waves had high energy. So a gamma particle is going to have a high amount of energy. Penetrating power. There's no charge, which allows it to only interact when it hits a collision. So gamma rays are going to be taking off and have a lot of penetrating power until they actually run into the nucleus of another particle. Nucleus are very, very small, so there's a lot of times it's going to go just right through something. So it's not going to hit any nuclei as it travels through. Artificial transmutation. All right, so our last slide. The bombardment of elements with alpha rays to make new elements. Beyond uranium in the periodic table are transuric, or synthetic elements. What that means is that they were an alpha particle. So we're going to say this is a proton, and this is a proton, and then 2 neutrons with this as well, was shot into some existing element. And when we got done, the new element had a new mass number and a new atomic number. The atomic number is really what's important because it's the atomic number we use to identify elements. So this new element was because it had either 1 or 2 or several more protons in its nucleus. Everything beyond uranium is transuric, or synthetic, meaning it's artificial. What I want you to understand is its half-lives are much less than the Earth's life, and that's why there's no longer here. They may have been here. These elements may have existed at one time, but because their half-lives are so much smaller than the Earth's lifespan, they're gone. They're no longer existed. They've either undergone alpha decay or beta decay or some type of gamma decay, and no longer are the same element. They've changed into some other element. And that's what we're saying right down here. So hopefully that leads you into some questions. If I was you, trying to find some math problems to work out there, is I would start all the way up here with uranium, and I would work my way through. All right, so we have uranium goes to thorium. Why? And I'd write that down. What is thorium going to go through then? Because it tells us that thorium, what does it say here? Here we go. Thorium is radioactive, and it's going to emit a beta ray, a beta decay. So what's it going to become after it undergoes that beta decay? Hey, that's just a thought for you. I'll see you on the flip side.